Good day, students. Welcome to our another online session for the course Digital Logic Design. In today's session, we will be discussing the canonical and standard forms of the Boolean functions, how we're going to generate the canonical form from the truth table, or how we're going to generate the standard form from the truth table, and how we can migrate from canonical to standard forms of expression. Since in our first discussion, we've said that any digital system can be represented in different ways. For example, we can have a Boolean function that can specify the relationship between the inputs and outputs, and that is the mathematical representation. Secondly, we can have a logical diagram that is a graphical representation that basically represents the resources and how we're going to implement any particular function to generate a particular output. Third is the timing diagram. Timing diagrams are also the graphical representations, and that tells us that how we're going to apply the inputs and how the output is generated. Basically, they are linking or associating the inputs with the outputs. And the fourth is the truth table. And we've said that we have to sometimes migrate from one standard form to another standard form. And for a computer science student, we must now know how to convert from one expression or one form of the digital system to another form. So to start our discussion, first of all, let us see the contents which we will be covering in today's session. So these are the contents. Basically, our discussion will be focused on some practical examples in which we will try to learn how to generate a Boolean function from a truth table, either in a canonical form of expression or standard form of expression. And if we've got a canonical form of expression, how we're going to convert that into the standard form of expression, we will learn in today's session. So as far as our discussions are concerned, this is chapter number 2. It's section 2.6 of the book of Digital Design with Introduction to Verilog HDL. And we will be discussing that shortly. But before discussing the canonical and standard forms of expression, let us first review the content which we have studied in the previous session. In our previous session, we have studied about some basic gates, and we've discussed about the primary gates as well as the universal gates, and also our emphasis was on the Boolean algebra, specifically the De Morgan theorem. We've discussed both variants of De Morgan theorem, and afterwards we've discussed how to represent multiple input gates, and what are the ICs and packages that are used to implement those on a commercial scale. So we've discussed that in detail. So to start with today's session, first of all, let us define the terms. What are the min terms and max terms? These are the two terms which you will hear a lot while discussing the canonical forms of expression. So what are the min terms and what are the max terms? We will discuss that, and we will generate min terms and max terms with example, and we will see how we're going to represent that by for a particular example. So we will construct a random example in order to explain the concept. But to before starting the explanation of min terms and max terms, let us review that if we have any Boolean variable or a literal, what are the two forms that Boolean variable can have? For example, let us assume that we have a Boolean variable a. So a can be represented in its true form, that is 1, and a can be represented in its complemented form 0. So if we are using the same literals as a representation, so we represent true form as a and the complemented form as a prime. So any variable can have a true form. This is the true form, and can have a complemented form. So if we see a 0 in an expression, we can replace that 0 with a prime. And if we see 1 in an expression and that expression belongs to the variable a, we can represent it with a. Now coming to the min terms and max terms, then we'll switch to the example and we'll see how we're going to represent the min terms and max terms. Min terms are also known to be the product terms. These are also known to be the standard product terms. As far as its name is concerned, if we have a system of three variable or three literals, then definitely we are constructing the product between all the literals, and the response of that product is always equals to 1 basically. So min terms are the terms that contributes 1 to the output of the function. So all the min terms definitely will contribute 1 to the output. As far as the max terms are concerned, max terms are known to be the standard sum terms, and max terms basically contributes 0 to the output of any function basically. So how we're going to represent min terms and max term? Let us discuss an example in which we're going to generate a truth table for the three literal system, and then we are going to define the response of the system, and then we're going to see what are the min terms and what are the max terms, and how we're going to extract those terms in order to produce a Boolean function. So let us assume that we have a system of three variable A, B, and C are the inputs, and let's assume the output is, for example, D in this particular scenario, where D is basically a function of A, B, and C. D is a function of A, B, and C. Okay, so let us first generate all the possible combinations of input. Since we've got three inputs, so how many combinations do we have in a truth table? That is 2 raised to power 3 equals 8 combinations, starting from 0 till 7. So we've got three inputs, A, B, and C. So the combinations are 0, 0, 0 for the first combination to represent the binary digit 0, then it's 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and the last combination is 1, 1, and 1. Now, how the minterms are represented? That are represented with small mi, and we're going to generate those minterms for each term, each input combination. So the first minterm is known to be the m0, small m0. This is m1. This is m2. This is m3. This is m4. This is m5. This is M6, and the last one is M7. Now, what would be the possible value of these min terms, as we have to extract those values from the truth table in terms of A, B, and C literals. Let me expand this table first. So the possible value of the min terms with respect to the literals are, so these are the min terms. Since we know that min terms are the terms that contributes 1 to the output, so if this first combination has to produce 1 in the output and we are using the AND operation, then we have to apply these in a complemented format basically. So A should be A prime, this should be A prime, this should be B prime, and this should be C prime. So if you see a value that is 0 in a truth table, you represent it in its complemented notation. And if you see a value 1 in the truth table, you represent it in the original notation, that is in the true form. And we have to construct the AND operation. So basically it's A and B and C. But since these are 0, so it should be A prime, B prime, and C prime. Now for the second combination, it's 0, 0, 1. So A should be in a complemented notation. A prime dot B prime, but C is 1, so C should be represented into the original notation. So it's A prime dot B prime dot C. Now if you take the product, it will contribute 1 to the output basically. Coming to the next term, that is A is 0, B is 1, and C is 0. So that is A prime dot B dot C prime. Next term is A prime dot B dot C prime. The next term is A into B prime into C prime. For M5, that is A into B prime into C. Then M6 is equal to A, B into C prime, and M7 equals to A into B into C. So these are the possible values of each of the combination of the truth table, and these are the min-term representation of those combinations. Now coming to the max terms. Max terms are represented with capital MI, and those are the terms basically that contributes 0 to the output when we are representing in terms of sum of min terms or product of max terms, which we will be discussing shortly. So first max term is known to be the capital M0, then is capital M1, then is capital M2, capital M3, capital M4, capital M5, then we've got M6, and then we've got M7, and the terms are basically, now one thing which you have to remember is that min terms are basically opposite to the max terms. So if we are taking 0, the literal is complemented in min terms, but in max terms it is being represented in its original format. So basically max terms are always complement to the min terms. So the first max term, since A0, B0, C0 is equal to A plus A or B or C. Since I have clearly said that max terms contribute 0 to the output and min terms contribute 1 to the output, so in order to produce 0 here, if A is equal to 0, B equals to 0, C equals to 0, automatically the OR operation between 0, 0, 0 is 0. For the next term, that is A plus B plus, now since we have to contribute 0 to the output, so what we have to do is we have to invert this C in order to produce 0, so that is equal to C prime. So what we are doing in min terms, we are doing totally opposite in the max terms. The next max term is A plus B prime plus C. The next is A plus your or operation B prime or C prime. For capital M4, we've got A prime since it's 1, or B, or C. The next is A prime or B or C prime. For M6, capital M6, that is equal to A prime or B prime or C, and the last term is A prime or B prime or C prime. And you can also associate these terms with respect to the De Morgan's theorem. You can verify that. So min terms are always the complement of max terms. Okay, so I hope so. If any table is given to you, you can easily now extract the min terms and max terms. Let me see if any example. This is article 2.6 of your book, and this table is basically table 2.3 of the book. Let me write it as a reference. This is table which we have discussed right now. This is table 2.3. Okay, so now let us see the two possible representations any Boolean function can have in a canonical form. Either the Boolean function can be represented in sum of min terms format, or the Boolean function can be represented in product of max term format. So we've got two representations, sum of min terms and product of max terms in canonical form. As far as the sum of min terms is concerned, its name implies that those min terms which are contributing 1 to the output, basically we have to OR those min terms. So if we represent by this notation that all those main terms which are contributing 1 to the output of the system are basically odd or summed, so that representation is known to be the sum of main terms. For example, we've got a function f that is equal to x prime, y prime, z, or x, y prime, z. So here you can see that in this particular Boolean function, we've got two product terms. There are two main terms. These are the two main terms, and we are basically ORing those main terms, so having a Boolean sum of those main terms. So if any function is represented in that particular format, that is known to be the sum of main terms. So to start with an example, let me generate an arbitrary function so that you can learn how to convert or how to generate the sum of min terms. One important thing which you should keep in your mind that either in a canonical form we can represent in sum of min terms or product of max terms. So you have got both the choices. You can, if you're comfortable with representing the function in sum of min terms, it's fine. And if you're comfortable with representing the function as a product of max terms, it's also fine, because both the functions will produce the same output. So to start with an example, and then we'll see what are the possible representations. For example, we've got a Boolean function. Starting with that exclusive OR gate. If you remember that exclusive OR gate, let us discuss the truth table of that exclusive OR gate, and let us see what would be the Boolean function of that that exclusive OR gate and how that function is being extracted basically. So we've got an exclusive OR gate that has two inputs, for example, A and B. And the output is Y, for example, and the possible combinations are 0, 0, 0, 1, 1, 0, and 1, 1. And if you remember the output of exclusive OR gate, what was the output? That was 0, 1, 1, 0. Okay, so first thing which you will gonna observe while observing that truth table is just encircle those combinations that are producing 1 to the output. So this was the combination that is producing 1 to the output. This is the combination that produces 1 to the output. So what we will do is we will extract those min terms basically from here and from here. So the first min term is A prime into B, or AND operation between the B, and the second min term is A into B prime. Now for the sum of min terms, as the name implies that we have to add or sum those, have a Boolean sum for those two terms. So what we will do is that we will basically OR these two terms. Now in this particular example, we have extracted a Boolean function from the truth table in the format of sum of min terms. We can also do a way around also. For example, we can convert that into the product of max terms, and the result would be same. So for the product of max term, let me just erase the first one. Oops, I've also erased the combinations in the truth table. Let me rewrite those also. Now for the product of max terms, the important terms that are being considered while generating the Boolean function are those terms which are basically 0. So this is the term and this is the term, and we will extract the max terms from the table. Now the first max term that is being extracted from this table is A or B, and from this table the term that is being extracted is A prime or B prime. So what we are going to do is we are basically gonna construct the OR operation between those terms. Sorry, not OR, it's AND operation because the name says product. Okay, so we are doing totally opposite what we are doing for the sum of many terms. So the expected function would be, that is A or B and A prime or B prime. Okay, so you can either represent your Boolean function in sum of min terms format, or you can represent in product of max term format. So let me see if I can have any example in which you can have practice for both sum of min terms and product of max terms. So we will be having example for product of max terms as well as for sum of min terms. Sum of min terms. Well, to start our example, let us assume that we've got a function of three variables, and the variables are k, l, and m, and the output of the system is a. So let me write the combinations first, that are 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1. Then we've got two more combinations, that are 1, 1, 0, and 1, 1, and 1. Okay, so let me define some random output in order to explain the concept that we can represent the function in both format. The thing which you can get from this discussion is how to extract the terms either in terms of main terms or in terms of max terms in order to convert or generate a Boolean function. That you should know, because sometimes we have to migrate from truth table to the Boolean function, or we have to generate the truth table from Boolean function. So we should know all the possibilities. And let us assume, for the sake of our implementation discussion, that we've got the output that is equal to 0 1 0 1 1 0 1 0. So I have written some random outputs. For example, we've got a system of three literals K, L and M, and output is A, and whenever we apply this combination we are getting this result. Okay, so how we're going to extract the Boolean functions and how we're going to represent those functions basically. So we've got, let me erase this highlighted section, and that was a basically the output. Starting with sum of main terms, we will extract those terms that are contributing one to the output. This is the term, this is the term, this is the term, and this is the term. So the first term is, so A can also be represented as, so keep in mind that I am just using sum of main terms. Then afterward I will use the product of max terms to represent the same function in its equivalent form. So the first term is K, it's 0, so it's K prime into L prime into M. Then we have to use OR operation between the terms, so we are using plus notation. The next term is K prime, this term into L into M. Then the third term is this one, it's K into L prime into M prime. And the fourth term is this one, that is K into L into M prime. Okay, so we can represent that also with respect to notations which you've studied before. So this one is K prime L prime M. This is M small m1 plus this is m3 plus this is m4 plus this is m6. We can also represent that Boolean function in that particular format, or we can represent that Boolean function A equals, mathematically we'll use this summation symbol, and we will index those terms basically that are contributing one to the output. So this is the term number 1 1 comma 3 comma 4 comma 6. So all these representations are basically equivalent or same, and they represent the sum of main terms. Now coming to the other representation, let me see if I've got some enough space here. So for the product of max terms, this A would be represented as, now in this particular scenario, the terms that are important to us are the terms that are contributing 0 basically for the product of max terms. This one, this one, this one, and this one. So A would be, the first term would be K or L or M, and this is product of max terms, so we'll generating the product terms, we are multiplying those terms. So we've got 4 product terms. The next term is K or, if you see that it's 1, so we are using L prime, or this is 0, so this is M. The next term would be K prime or L or M prime, and the last term is K prime or L prime or M prime. Or we can also represent this Boolean function as, this is capital M0 multiplied by, this is capital M2 multiplied by capital M5 or AND operation. This is capital M5 and then capital M7. And we can also represent this function in the product of maxterm format as A equals this pi symbol. This pi symbol basically represents the product of max terms, and we will provide the index of those terms. So 0, 2, 5 and 7. Now we've got two different functions of the same truth table. So either we can represent that in sum of min terms format, this is sum of min terms, or we can represent in terms of product of max terms, so this is product of max term representation. Okay, so basically sum of min terms and product of max terms are totally opposite to each other. Sum of min terms are opposite to product of max terms. So you've got both options. Either you can represent in sum of min terms format, and you can also use the product of max terms format. With which format that seems convenient to you, you can follow that notation to represent your Boolean function. Now we can easily convert between the canonical form and standard form. So what we have to do is, in order to convert from the canonical form and standard form, is that if you have got sum of min terms format, the expression is in sum of min terms format, then you will first of all extract those expressions. The first step is to extract those expressions in terms of min terms, in terms of min terms, that are contributing 0 to the output. The next step is take its complement by using De Morgan theorem or general function complement. Take its complement. Now you will get by this step your sum of min terms is being converted into the product of max terms, and same process you will apply while converting from product of max term to sum of min terms, and you will do the opposite work. For example, you will from the product of max term you will extract those max terms that are contributing 1 to the output other than 0, and then you're gonna take the complement of those max terms to produce the sum of min terms. This is basically defined on page number 55 of your book with an example of the conversion and the subscript they've used So you have to go to the page 55 in order to see the example. Now coming to the standard form of expressions are also the same, similar to the canonical form, except that in that particular format, it's not necessary that each term, either it's the main term or the max term, would have all the possible literals that are present in that term. So we can represent that into two possible representations as sum of products, just like sum of min terms, known as SOPs, sum of products. And the second form is product of sum, just like the product of max terms. So basically these forms are equivalent. Sum of min terms is basically the sum of product term, and sum product of max term is basically the product of sum. But you have to be sure that every canonical form is a standard form, but it's not true that every standard form is canonical form, but we can convert those from standard forms to canonical form and canonical forms to standard form. The example is, for example, we've got a function f is equal, that is also three literals, for example, literal a or b into c or a into c. This is the sum of products format. For example, we've got the product term a multiplied by 1, b into c and a into c. You can see that for the first term we don't have b and c available here. For the second term we don't have a available here. For the third term we don't have b available here. So sum of products are the summation between the product terms, and it's not necessary that each literal is appearing in each product term. So this is the minor difference between sum of min terms and sum of products. Otherwise both are same basically, and the minor difference which I've stated earlier. Same is the case with product of max term. For example, in that particular case we've got same three literals function. We've got f is equal to a or c multiplied by b or c. So we've got two summation terms. These are not the max terms. So be very careful, because the b literal is not available here and a literal is not available here. For min terms and max terms, all the literals should be available in each product term or sum term. So basically we are generating the product between two sum terms. So basically both the representations are similar to each other. The standard forms are basically the simplified forms as compared to the previous ones, because they are having a less number of literals in that. Well, that was all for today's discussion. I hope so. Now you are able to convert or generate the standard forms as well as the canonical forms. You can use both representations, and which representation seems convenient to you, that is preferred. But as far as the simplification and implementation of Boolean functions with lesser number of variables is concerned, we have to generate a simplified Boolean function. Either it's in a canonical form or a standard form. So if it is in a canonical form, the simplified function will always be in a standard form. So we should know now how to simplify those, and we will learn later on in our later stages in our class that how we're gonna simplify the Boolean functions. Either we are using Boolean algebra or we are using K-maps or some other dedicated techniques in order to migrate from one form to another, and in order to simplify our Boolean function. Why we need to do simplification? Because we have to implement our Boolean function with the lesser number of resources. Lesser the resources, or lesser the cost of implementation cost of the circuit, and the circuit is economical. Well, students, that was all for today's discussion, and in our next discussion, we will be focusing on the universal gates implementation, and we will see different examples that how we're going to implement a Boolean function by using universal gates only. Till now, have a good day. Take care. Allah Hafiz.